we've talked about how stars the size of the sun die. Stars bigger than 4 solar masses, though, are going to do an extra step of nuclear fusion. And they will fuse this carbon into something else, neon. And but as long as these original stars less than 8 solar masses, what's going to happen is it will spit off so much stuff as it's dying that what is left is simply going to be a white dwarf. And so these white dwarfs, are typically not going to be all that big. They're going to be about 2/3 of a solar mass or less. Between 0.5 and 0.6 solar mass is pretty typical. If they're part of a binary system, they can actually pull in some gas from the binary component, and that can make them a little bit bigger. But overall, 1.4 solar mass is the biggest the white dwarf can be, but the vast majority of them are considerably smaller than that. For the stars bigger than 4 solar masses, then they will actually fuse a little bit more. If they get above 600 million Kelvin in the center, the carbon will fuse into neon, and you can actually it'll fuse into neon, and then the neon will go on, and then the surplus helium spit out by the neon fusion here can actually fuse with the carbon and make oxygen. And so we'll get a neon and oxygen sort of core. Okay, so what will happen though is that for a smaller star, it's going to have this carbon-oxygen core, hydrogen on the outer parts of the star. Okay, we have the hydrogen fusing shell, we have the helium fusion shell, and then a carbon core in the middle. Just kind of a dead core. This is how the sun is going to die. The core is not going to fuse anything beyond carbon and a little bit of oxygen. It's just going to be the dead stuff left over. Okay, but bigger stars, like I said, they will fuse some of that carbon into neon. So what will happen is you'll have some neon in there. Okay, and now you can expand again to be a red giant, and it'll become a red supergiant. Okay, so the core will be fusing, and then what will eventually happen though is that you're going to have the outer parts. The outer parts always say hydrogen helium. You have a hydrogen fusion shell, helium, which falls in the lower shell, which is helium fusion, which makes carbon, which falls into the lower shell. That carbon is going to be fusing, and it's going to be fusing into neon. You'll have a little bit of carbon produced in here as well. The helium fusion makes some carbon and some oxygen, and then the carbon will fuse a little bit and make more oxygen. And so you get an oxygen neon core. Again, it's going to be dead at this point, and then what you'll have is when you blow the outer layers off into space, then you're going to have a oxygen neon-rich white dwarf star. All right. But for stars bigger than 8 solar masses, the core is going to get even hotter. Before you get rid of the outer layers, the core is going to actually get hot enough to fuse neon. So at about 1.5 billion Kelvin, neon fuses. Neon will fuse into oxygen and magnesium. So we're building up a whole bunch of oxygen in the core of all of this. Okay, and so you end up with this neon and oxygen. The core becomes actually magnesium and oxygen in there. Okay. Now I didn't really mention magnesium because it just kind of gets in the way. At 2 billion Kelvin, the oxygen will fuse into silicon, and then you get a spare helium in there. That helium can go actually fuse with other things. So you start making extra isotopes of things at this point. And so 2 billion Kelvin. And you say, well, what kind of stars do that? Well, anything bigger than 8 solar masses will keep this process going. It'll get hotter and hotter and hotter in the core. It's got so much energy and so much heat that it doesn't really ever become a degenerate gas. It just gets more and more compact and more hot and starts the next process of fusion. Eventually, the silicon itself will fuse once you get to 3.5 billion Kelvin. It fuses into nickel 56. Well, nickel 56 is going to be something that will, if it gets slammed by an electron, then what will happen is, again, above 6 to 9 billion Kelvin, it will actually do what we call inverse beta decay and spew out a neutrino and become cobalt 56, which quickly grabs another electron and becomes iron 56. Okay, now at that point it is inert because that means that any further fusion turns out that it doesn't release enough energy to sustain itself. The whole process that's happening inside the sun or any star here is that the process of nuclear fusion, when you squeeze the atoms together, that releases so much energy it pushes against the squeezing. If you try to squeeze past iron, what happens is it uses up energy, which makes it cooler, which actually stops the fusion. And so you don't actually fuse past iron. Okay, but a really massive star, one bigger than 8 solar masses, will keep fusing. It'll eventually have the outer parts stay hydrogen helium. They never did any fusion. And then the inner core has been fusing, but as it shrinks, you have these shells that are fusing above it. So for our outermost shell is going to be hydrogen fusing into helium. Okay, that helium is heavier, so it sinks, and you have a helium fusion cell, which creates carbon and oxygen. That sinks in here, okay, fuses neon, carbon to neon, okay, and that neon and oxygen are still in there. Eventually, what happens is it gets so hot, the oxygen starts fusing, and then the silicon starts into silicon. The silicon starts fusing into iron, and the iron core builds up. It builds up until you get 1.6 solar or 1.4 solar masses. Once you get 1.4 solar masses, again, Chandrasekhar limit, then electron degenerate pressure cannot hold it, and then it goes into a violent collapse in which it collapses in just a fraction of a second from something almost the size of the Earth down to something the size of Arlington, and releases enormous amounts of gravitational energy when it does that. Also releases a lot of thermal energy, a lot of nuclear fusion has to happen. You have to squeeze all these electrons and protons together, inverse beta decay with all this, and so what happens is you spew out unbelievable numbers of neutrinos. The whole process we call a supernova. We'll get back to that later. But here we have kind of a schematic of a red supergiant star. The outer parts of that star are all hydrogen and helium, and everything happening is happening right in the core. This tiny little area about the size of the Earth is where everything is, all the activity is happening. Okay, and yet the outer edge of the star stretches all the way out to about Jupiter's orbit around the sun. So all the stuff that's happening in the middle, you can never see. So here's kind of a recap of the different fusion processes that happen in there.